Imagine being able to leap through time, viewing the universe as it was 13.5 billion years ago. This is not a science fiction plot, but the reality of what the James Webb Space Telescope enables us to do. Thus, for the science community, the successful launch of James Webb was a heart-swelling moment, akin to witnessing the first steps of a giant leap for humankind. But while the telescope did indeed perform magnificently, far exceeding all expectations in several ways, some troubling observations have been reported. It seemed to have found galaxies completely unexplained by accepted theory. Astronomers worried that our understanding of the universe's early moments was fatally flawed and cosmology broken. Some press reports even hinted that the Big Bang was wrong. Things took a turn for the worse when the latest discoveries of Webb continued to provide compelling clues that something might be amiss and the model might need to be updated. Join us as we dig deep into how the latest results from James Webb just triggered something of a crisis in cosmology. The James Webb Space Telescope is the worthy successor to the legendary Hubble Space Telescope, but it's like comparing a biplane to a stealth fighter. Its mirror, 6.5 meters in diameter, captures 7 times more light than Hubble's 2.44-meter mirror. These space-based telescopes allow us to peer deeper into the cosmos, past the atmospheric limitations and infrared interferences that Earth-bound telescopes face, and to bring the universe to our doorsteps in unparalleled detail. The story of cosmology given to us by the Standard Model says that about 400,000 years after the Big Bang, electrons and protons found each other to create the first hydrogen atoms. Before this, they had been running free along with the photons that would soon become the cosmic microwave background radiation. Once this recombination into hydrogen occurs, the universe is largely composed of a fairly smooth gas of these atoms with some helium around too, and the leftover background radiation. Now gravity can get to work within perturbations, small regions of overdensity in the hydrogen gas, and slowly collapse them to form the first stars. It is inside these first stars, which are formed only of hydrogen and helium, that nuclear fusion begins to forge all the heavy elements we know today. Elements like carbon and nitrogen play an important role in the story of galaxy formation. That is because these are the elements that can absorb heat from surrounding gas and emit photons that cool that gas. This cooling process will be critical in helping gas coalesce into galaxies. Eventually, these first-generation stars explode, and the resulting supernovae seed the gas that surrounds them with heavy elements. Each supernova, along with black holes which are also forming, pumps ultraviolet radiation into the universe. This strips electrons from hydrogen atoms, making the universe more and more transparent to UV radiation. After the universe has run through a few generations of stars, there are enough heavy elements and UV radiation around to feed the formation of galaxies. Stars and vast quantities of gas collapse into gravitationally bound entities to pull these first galaxies together. This is a good story, and observations confirm key parts of it. The problem comes when it is placed within the cosmological context of the expanding universe. The Standard Model of cosmology gives astronomers a way to link the observed distances to objects, expressed in redshift, with their age relative to the Big Bang, expressed in years. Distances are measured by observation and cannot be tinkered with. Age, on the other hand, comes from a theoretical story. We take our models of an expanding universe guided by. Directly after pointing James Webb's near-infrared spectrograph instrument towards the source of the explosion, the researchers found signatures of elements such as oxygen and calcium, which are commonly found within supernovas. But they didn't find any elements heavier than iron among the debris, potentially ruling out bright explosions such as the boat as heavy metal producers. Surprisingly, despite the extreme brightness of the gamma-ray burst, the supernova it came from was of fairly average brightness. It's possible, according to the researchers, that the boat acquired its extraordinary intensity from the exploding star's material being funneled along an unusually narrow relativistic jet, a near-light speed stream of charged matter. In the words of co-author Tanwi Lasker, an assistant professor of physics at the University of Utah, it's like focusing a flashlight's beam into a narrow column as opposed to a broad beam that washes across a whole wall. In fact, this was one of the narrowest jets seen for a gamma-ray burst so far, which gives us a hint as to why the afterglow appeared as bright as it did. There may be other factors responsible as well, a question that researchers will be studying for years to come. The researchers say their next steps will be to use the Webb telescope to look at other supernovas. Contrasting their different brightnesses, jets, chemical elements, and host galaxy characteristics could help them figure out just how unusual the boat was and the conditions under which the universe's heavy elements are made. In another finding, researchers may have solved the mystery of why a distant galaxy surrounded by an eerily perfect Einstein ring is denser than it should be. The Hefty galaxy, which was discovered by the James Webb Space Telescope, is being compressed by a massive halo of dark matter. Einstein rings, which were first predicted by Albert Einstein's theory of relativity, are luminous halos created by a phenomenon called gravitational lensing. This occurs when light from a distant object is warped around a foreground object located directly between the distant object and the observer. The light looks as if it is being bent by gravity, but in reality, the light is traveling in a straight line through spacetime that has been warped by the foreground object's hefty mass. In September 2023, astronomers discovered an Einstein ring named JWST R1 in data collected by James Webb. The luminous structure has two parts, JWST-E1R, which is the actual luminous ring made of light from the distant galaxy, and JWST-E1G, which is the foreground object that lenses the distant galaxy's light. JWST R1R is around 21 billion light-years from Earth, making it the most distant gravitationally lensed object ever discovered. After adjusting for the universe's expansion rate, researchers estimated that the galaxy was born about 10.3 billion years ago, or around 3.4 billion years after the Big Bang. At the time of this discovery, researchers noticed that the lensing object, JWST R1G, was unusually dense. The size and shape of the ring surrounding this galaxy suggested that it had a mass of around 650 billion suns, which is very high for a galaxy of its size. A large amount of this mass is likely dark matter, a mysterious form of matter that does not interact with light but makes up around 85% of all matter in the universe. But even when this mysterious substance is accounted for, the galaxy still seems too massive for its size. The researchers wrote in a paper at the time that additional mass is needed to explain the lensing results. However, they provided no explanation for what this additional mass could be. But in a new study published in the Astrophysical Journal Letters, a new group of researchers has proposed an explanation for JWST-ER1G's unusual density. A halo of dark matter surrounding the galaxy is being compressed into an ever tighter space as regular matter collapses into it, resulting in a higher density of the mysterious substance. As study lead author Do Kong, a researcher in the Physics and Astronomy Department at the University of California, Riverside, said in a statement, "Our numerical studies show that this mechanism can explain the high dark matter density of JWST R1G. This is not the first true Einstein ring spotted with James Webb." In September 2022, a Reddit user tapped into the telescope's data to reveal a perfectly circular ring of light roughly 12 billion light-years from Earth. James Webb has also utilized gravitational lensing to snap the most distant star ever detected in some of the universe's oldest galaxies. The researchers hope the telescope can help identify more Einstein rings to test their theory further. As study co-author Hibu, a professor in the Physics and Astronomy Department of the University of California, Riverside, said in the statement, "The James Webb Space Telescope provides an unprecedented opportunity for us to observe ancient galaxies formed when the universe was young. We expect to see more surprises from James Webb and learn more about dark matter soon." Interestingly, besides deep space discovery, the Milky Way has a newfound black hole, and it lurks close to Earth. This sleeping giant was discovered with the European Space Telescope Gaia, which tracks the motion of billions of stars in our galaxy. Stellar mass black holes are created when a large star runs out of fuel and collapses. The new discovery is a landmark, representing the first time that a big black hole with such an origin has been found close to Earth. The stellar mass black hole, designated Gaia BH3, is 33 times more massive than our Sun. The previous most massive black hole of this class found in the Milky Way was a black hole in an X-ray binary in the Cygnus constellation whose mass is estimated to be around 20 times that of the Sun. The average stellar mass black hole in the Milky Way is about 10 times heftier than the Sun. Einstein's general relativity and our understanding of matter as expressed in the standard model of particle physics together tell us how a distance or a redshift correlates with an age, a time since the Big Bang. So, what is the problem? Almost as soon as James Webb was turned on, it found galaxies at redshifts and hence ages much farther back than the standard model of cosmology predicts. Here is how the problem plays out. With Webb's images, we are looking very, very far away. Since looking to a particular distance means looking back in time, we are also looking very, very far back in time. But the universe has a beginning called the Big Bang. The age-redshift relation, which comes from the standard model, tells us how to convert an observed distance into a time after the Big Bang. But there seems to be a mismatch between how old these first galaxies appear to be and how long ago the age-redshift relation tells us they must have formed. Well-formed galaxies are appearing too early for the story we told above to fully play itself out. The Big Bang model of cosmology shows us a universe that is evolving rather than static and eternally unchanging. It is not under question in any serious way. What these new James Webb results do throw into question is the story about that evolution that the standard model of cosmology tells us. But at that time, some researchers, rather than create a new theory of cosmic evolution, suggested that the presence of gigantic early stars could explain the observation of unexpectedly bright early galaxies. Stars in the modern era tend to be comparable in mass to our Sun. However, these researchers postulate that stars in the early universe could be 100 times the mass of the Sun. Such massive stars would be extremely bright, and relatively few bright early stars would look much like many more modern stars. This could explain the reports of early massive galaxies. Another possible solution involves the mechanism whereby hydrogen and helium gas clouds become stars. In the modern day, these clouds form stars with a well-known probability. If astronomers see a certain amount of star formation in a recent galaxy, they can estimate the amount of hydrogen gas in the galaxy and determine its mass. However, perhaps in the early universe, star formation was more efficient, and it proved easier for clouds to become stars. If that were true, then observations of early star formation would lead astronomers to estimate that the gas clouds in early galaxies were larger than they actually were. The result would be that scientists were fooled into thinking that early galaxies were larger than reality. However, these doubts were quickly quelled when the latest discoveries of James Webb provided compelling evidence that there was a crisis in cosmology and the standard model might need to be updated. In a groundbreaking observation, the Webb telescope has found a galaxy in the early universe that's so massive it shouldn't exist, posing a significant challenge to the standard model of cosmology. According to the study authors, the galaxy called ZFS 7329 contains more stars than the Milky Way despite having formed only 800 million years into the universe's 13.8 billion-year lifespan. This means they were somehow born without dark matter seeding their formation, contrary to what the standard model of galaxy formation suggests. How this could have happened is unclear, but much like previous Webb discoveries of other inexplicably massive galaxies in the early universe, it threatens to upend our understanding of how the first matter in the universe formed, or possibly even the standard model of cosmology itself. The researchers published their findings in the journal Nature. According to study co-author Claudia Lagos, an associate professor of astronomy at the International Center for Radio Astronomy Research, having these extremely massive galaxies so early in the universe is posing significant challenges to our standard model of cosmology. This is because massive dark matter structures, which are thought to be necessary components for holding early galaxies together, did not yet have time to form this early in the universe. Lagos added, light travels at a fixed speed through the vacuum of space, so the deeper we look into the universe, the more remote light we intercept and the further back in time we see. This is what enabled the researchers to use James Webb to spot ZFS 7329 roughly 11.5 billion years in the past. By studying the spectra of light coming from the stars of this extremely distant galaxy, the researchers found that the stars were born 1.5 billion years prior to that observation, or roughly 13 billion years ago. Astronomers aren't certain when the very first globules of stars began to clump into the galaxies we see today, but cosmologists previously estimated that the process began slowly within the first few 100 million years after the Big Bang. Current theories suggest that halos of dark matter, a mysterious and invisible substance believed to make up 25% of the present universe, combined with gas to form the first seedlings of galaxies. After 1 billion to 2 billion years of the universe's life, the early protogalaxies then reached adolescence, forming into dwarf galaxies that began devouring one another to grow into ones like our own. But the new discovery has confounded this view. Not only did the galaxy crystallize without enough built-up dark matter to seed it, but not long after a sudden burst of star formation, the galaxy abruptly became quiescent, meaning its star formation ceased. According to study co-author Thea Nayakar, an astronomer at the Swinburne University of Technology in Australia, this pushes the boundaries of our current understanding of how galaxies form and evolve. The key question now is how they form so fast very early in the universe and what mysterious mechanisms lead to stopping them forming stars abruptly when the rest of the universe is doing so. The researchers' next steps will be to search for more galaxies like this. If they find any, it could seriously contradict prior ideas of how galaxies formed at that time. The real question facing us is how much of an update for our standard model of cosmology is needed. In the meantime, note that while James Webb has created a few more puzzles, it has solved a lot. In a remarkable revelation, the Supreme Observatory has discovered the cause of the most powerful cosmic explosion since the Big Bang. The explosion, nicknamed the boat or brightest of all time, is a gamma-ray burst that spat photons at Earth with more energy than those found inside the Large Hadron Collider. This light was detected by telescopes in orbit and on the ground on October 9, 2022. And came from 2.4 billion light-years away in the constellation Sagitta. Now, a team of scientists has tracked down boat's likely origins to a gigantic supernova that came after the collapse of a giant star. However, their research reveals a new mystery. Supernovas, such as the one behind boat, are supposed to be cosmic factories for heavy elements such as platinum and gold. But when the researchers looked, they found no evidence for them. The scientists published their findings in the journal Nature Astronomy. According to lead study author Peter Blanchard, an astrophysicist at Northwestern University, when we confirmed that the gamma-ray burst was generated by the collapse of a massive star, that gave us the opportunity to test a hypothesis for how some of the heaviest elements in the universe are formed. Yet, we did not see signatures of these heavy elements, suggesting that extremely energetic gamma-ray bursts like the boat do not produce these elements. That doesn't mean that all gamma-ray bursts do not produce them, but it's a key piece of information as we continue to understand where these heavy elements come from. When a massive star runs out of fuel, it collapses before exploding outward in a gigantic supernova explosion, leaving behind an ultradense neutron star or a black hole. It is these stellar explosions, and occasionally even collisions between two neutron stars that produce powerful bursts of gamma rays that can be picked up by observatories in space and even on Earth. The first gamma-ray bursts were detected accidentally by U.S. military satellites in the 1960s. Since then, they have continued to ping up on equipment that is able to detect their high-energy light. But when the boat appeared, it was at least 10 times brighter than any other cosmic explosion ever witnessed. And in the words of Blanchard, the event produced some of the highest energy photons ever recorded by satellites designed to detect gamma rays. This was an event that Earth sees only once every 10,000 years. In fact, the burst was so bright that it obscured any potential supernova signature in the first weeks and months after the burst. At these times, the so-called afterglow of the gamma-ray burst was like the headlights of a car coming straight at you, preventing you from seeing the car itself. Thus, the astronomers had to wait 6 months for it to die down before they could use the James Webb Space Telescope to look at it. Gaia BH3 is located just 2,000 light-years from Earth, making it the second closest black hole to our planet ever discovered. The closest black hole to Earth is Gaia BH1, also discovered by Gaia, which is 1,600 light-years away. Gaia BH1 has a mass around 9.6 times that of the Sun, making it considerably smaller than this newly discovered black hole. As George Seabrook, a scientist at Mullard Space Science Laboratory at University College London and a member of Gaia's Black Hole Task Force, said in a statement, "Finding Gaia BH3 is like the moment in the film The Matrix where Neo starts to see the Matrix. In our case, the Matrix is our galaxy's population of dormant stellar black holes, which were hidden from us before Gaia detected them." Seabrook added that Gaia BH3 is an important clue to this population because it is the most massive stellar black hole found in our galaxy. Of course, Gaia BH3 is a small fry compared to the supermassive black hole that dominates the heart of the Milky Way, Sagittarius A*, SGR A*, which has a mass 4.2 million times that of the Sun. Supermassive black holes like SGR-A** aren't created by the deaths of massive stars, but rather by mergers of progressively larger and larger black holes. All black holes are marked by an outer boundary called an event horizon, at which point the black hole's escape velocity exceeds the speed of light. That means an event horizon is a one-way, light-trapping surface beyond which no information can escape. As a result, black holes don't emit or reflect light, meaning they can only be seen when they are surrounded by material that they gradually feed on. Sometimes this means a black hole in a binary system pulling material from a companion star, which forms a disk of gas and dust around it. The tremendous gravitational influence of black holes generates intense tidal forces in this surrounding matter, causing it to glow brightly, with material that is destroyed and consumed also emitting X-rays. Additionally, the material the black hole doesn't feast on can be channeled to its poles and blasted out as near-light speed jets, which are accompanied by the emission of light. All of these light emissions can allow astronomers to spot black holes. The question is, how can dormant black holes that aren't feeding on gas and dust around them be detected? For instance, what if a stellar mass black hole has a companion star, but the two are too widely separated for the black hole to snatch stellar matter from its binary partner? In cases like this, the black hole and its companion star orbit a point that represents the system's center of mass. This is also the case when a star is orbited by a light companion, such as another star or even a planet. Orbiting the center of mass results in a wobble in the motion of the star, which is visible to astronomers. Because Gaia is adept at precisely measuring the motion of stars, it is the ideal instrument to see this wobble. Gaia's Black Hole Task Force set about looking for odd wobbles that couldn't be accounted for by the presence of another star or a planet and that indicated a heavier companion, possibly a black hole. Homing in on an old giant star in the constellation Aquila, located 1,260 light-years from Earth, the team found a wobble in the star's path. That wobble suggests that the star is locked in orbital motion with a dormant black hole of exceptionally high mass. The two are separated by a distance that ranges from the distance between the Sun and Neptune at their widest and our star and Jupiter at their closest. It's a real unicorn, lead researcher Pasquale Panuzzo of CNRS Observatoire de Paris in France said in a statement. This is the kind of discovery you make once in your research life. So far, black holes this big have only ever been detected in distant galaxies by the LIGO-Virgo-Cagra collaboration, thanks to observations of gravitational waves. Thanks to the sensitivity of Gaia, the Black Hole Task Force was also able to put constraints on the mass of Gaia BH3, finding it to possess 33 solar masses. Gaia BH3 is the very first black hole for which we could measure the mass so accurately, said Svi Mazza, a scientist and Gaia collaboration member at Tel Aviv University. At 30 times that of our Sun, the object's mass is typical of the estimates we have for the masses of the very distant black holes observed by gravitational wave experiments. Gaia's measurements provide the first undisputable proof that stellar mass black holes this heavy do exist. However, the Gaia BH3 system is bound to be of great interest to scientists for more than just its proximity to Earth and the mass of its black hole. The star in this system is a subgiant star that is around 5 times as large as the Sun, with 15 times its brightness. Though it is cooler and less dense than our star, the Gaia BH3 companion star is mainly composed of hydrogen and helium, the universe's two lightest elements, lacking heavier elements, which astronomers somewhat confusingly call metals. The fact that this star is metal-poor suggests that the star that collapsed and died to create Gaia BH3 also lacked heavier elements. Metal-poor stars are expected to shed more mass than their more metal-rich counterparts during their lives, so scientists have questioned if they can maintain enough mass to birth black holes. Gaia BH3 represents the first hint that metal-poor stars can indeed do so. As Seabrook concluded, Gaia's next data release is expected to contain many more, which should help us to see more of the matrix and to understand how dormant stellar black holes form. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, Thanks for watching, and we will see you next time.